Having learned about viscosity, let's consider now what happens when the coefficient of dynamic viscosity, mu, is constant. So when the coefficient that tells us how sticky the fluid is, if it's just a number, a constant number, what does that tell us about the character of the equations when viscosity is present? To get a handle on this, we're going to spend some time going in and out of Einstein notation. And this is a very handy tool for doing vector manipulations for a complicated system like this divergence of two tensor that's entering in as the force effectively in our momentum equation. So let's figure out what is the right hand side of this equation minus 1 over rho div dot pi ij. And to do that, we're going to write the contraction of our gradient, the dot product, as in Einstein notation. So we have to choose whether we contract on the I or the j. It turns out that the viscous stress tensor, the pi ij, is a symmetric stress tensor because I can swap the I and the j and everything ends up looking as it was before. So this means fundamentally I have freedom to contract on either one. And for simplicity, I'm going to contract on j and have I be sort of our remaining vector direction. When we contract on a tensor, it reduces the tensor in rank by 1. And so this 2 tensor, when contracted, is going to form a 1 tensor, which corresponds with our velocity vector that we're used to thinking about. So let's write out our tensor in the Einstein notation form. So that's d sub u I d sub x j plus d sub x d sub u j d sub x I, and then minus 2/3 d u k dx k with the delta ij here. Okay, so we can see, I was saying a moment ago that this thing's symmetric. There are pi ij. Oh, and I've forgotten our mu. Our mu is a constant, and so our mu propagates through the d sub xj term, and we just get a nice mu out front. And we've got this mu over rho term out front in our system. I said before that our pi ij was symmetric. So this part is symmetric, and you can see that because you can take any of the i's and j's, and I could rewrite all my j's as i's and all my i's as j's. So let's just do that for fun. So if I make this j, and I make this I, and I make this I, and I make this j, and I make this j, and I make this I, then my equation hasn't changed at all. And one reason that it's symmetric is that it is a plus sign in between these two terms here rather than like a minus sign. If it was a minus sign, having done this this transpose operation, I'd have a completely different equation. Okay, so with our contracted term on here, let's start propagating this through and rewriting this in a couple different ways to get some intuition about it. So first of all, this, sorry, I forgot, I've made a sign error here, right? Because this is minus 1 over rho, and pi ij, this actually has a minus mu inside of it. Let's make sure our earlier writing of it is correct. Yep, our earlier writing of it has the correct sign. So here, this should have actually been a plus sign because the minus sign here and the minus sign here annihilate each other. So we have our leading term here. This is mu over rho. And now let's start combining terms so we can get some intuition. So our first equation is d sub u I, and the d sub x j here, that contracts on the other d sub x j. So this is kind of like a d sub x j squared. And we can see that this whole thing looks an awful lot like a second derivative operating on our vector u here. All right, let's look at our other terms. So now we have our d sub uj, and we have our d sub xj on our d sub xi. We'll come back to that in a moment. And then we have a minus 2/3 d sub xj, and this is going to actually contract on the ij, and then we have our duk dxk. All right. So how can we simplify some things? Well, first of all, let's look at this term here. So we've got d by dxj dxi uj. But we can reorder these partial derivatives, the j derivative and the I derivative. These are independent derivatives. So we can reorder this, right? We can write this as duj dxi dxj. I can take the derivatives in different orders. And this is the same as d by dxi operating on duj dxj, just putting in a parentheses to kind of draw our attention to things. Well, that's very interesting because here we actually have a repeated index. We have the j is showing up 2 times here, and that means that we have a summation over all possible j's. And so calling it j was just pretty arbitrary. I can come in and relabel that, and let's relabel it the same way we've labeled things before. Let's relabel our contracted index here as a set of k's. So this is a sum, and I've used k because we used k up here for our sum, and that means that it reminds us it's a sum rather than j. Previously, j had been one of our pointing directions for our 2 tensor. Often in Einstein notation, you'll use letters like I and j for the pointing direction, maybe even sometimes k. And then you'll use a different set of letters like the k's or maybe l, m, and n or other things like that as your ones you're summing over. And different fields have different conventions. Just be careful in your own work that you choose a convention and stick to it in any particular set of analysis you're doing. All right. So we've made this term look a lot now like this term. And in fact, this gets even more clear when we consider this last term, this minus 2/3 d by dxj sigma ij duk dxk. Well, this is just a contraction, and this is just some thing, right? So we can just throw some parentheses around this so this looks kind of the same as up here, and we have the same kind of sense to this thing. Let's now think about what happens here as our xj contracts with this delta ij, our Kronecker delta. So what's the delta ij do? As a reminder, delta ij, right? This takes one of 2 values. This is 1 if I is equal to j, and it's 0 if I is not equal to j. So this basically just says, come in here, come into this part, and look anywhere you've got a j, and if that j is equal to an I, then these are going to be the same, and if it's not equal to an I, then it's going to be equal to 0. So what that really means is we can do some eraser math, and we can just erase our Kronecker delta here, and we can erase our j and just force our j to always be i's. Because we know that any time the j is not an I, then the Kronecker delta itself will be 0, making the term 0. And the only time that it's not 0, it's equal to 1. So it vanishes away and rewrites the j's as i's. Okay, let's now take these terms, this term here and this term here, and let's put them back into our main equation that we started with. So let's write it back down again, get some clarity here. So we have our mu over rho, we have our d ui, we have our dx. I'm going to take the liberty of relabeling the k's down here too. xk. We now have plus d by dxi on duk dxk. And then we have minus 2/3 on d by dxi on the same thing, duk dxk. Okay. Well, these are the same, so these two combine, and these just become 1/3 of this d by dxi on the quantity duk dxk. Let's put our squared up here to remind ourselves that two derivatives have hit our velocity vector u here, with these two derivatives being here and here, and where we've left them explicitly as repeated k summations rather than turning this, for example, into, as we might normally write it, like d sub xk squared as the second derivative in the k direction of x. We're writing out both of them here so that we remember it's actually a sum over all such directions. Okay. Well, this is nice. Let's write this now in vector form. So the Einstein notation has brought us to a correct expression for this quantity, minus 1 over rho div on pi ij. That's equal to all of this. But what's this equal to in a vector form, which can sometimes give us more intuition? Well, this minus 1 over rho div on pi ij, this is equal to mu over rho, and we have our second derivative term here. That's going to be, this is a Laplacian on the vector u, and then this term here, this is a gradient. The vector information in the I is located in the gradient. This is a 1/3 of a gradient on the quantity div of u. And we can see divergence of u by looking at this derivative contracted on u and summed in the k direction, and recognize that that's a gradient dotted with our vector u and then summed over all possible values, which is what the dot product contraction does. So in the case when mu is constant, and it's just a number, we've arrived at a form of our viscous stress tensor that is quite interesting. It actually is a Laplacian on our velocity. Let's write this back in the momentum equation and then pause and reflect on what it tells us. So writing our momentum equation, d by dt of u plus u dot grad u plus, here we're just considering the pressure forces. We're neglecting body forces for now, but they can easily be added on without modifying the viscous part of this equation. Mu over rho times the quantity Laplacian of u plus 1/3 grad on the divergence of u. This is the Navier-Stokes equations. Navier-Stokes for constant viscosity, and I also mentioned no what's called bulk viscosity. I think I'm getting the term on that right, and I'll double check. This second term that we're neglecting is a viscosity that operates very, very strongly on compression of the fluid in particular. So this form, though, this is the one that gets us the character of viscous flow when we just have frictional forces. Let's do one last rewriting of the system. What if we're also incompressible in addition to the rest? Well, in that case, our last term here, that goes to 0, and so we're left with the following. For an incompressible Navier-Stokes equation with constant dynamic viscosity mu, we have d by dt of u plus u dot grad on u plus the divergent or the gradient of the pressure divided by the density. This is all equal to mu over rho, now just the Laplacian on u. And we can tell now the character of what diffusion does by looking at our first term, d by dt of u vector. This is proportional to mu over rho del squared u. And we can recognize that that has classes of solution. So u scales as some u at some initial time, t naught, and then some exponential decay in time, e to the minus t over tau, where this tau timescale is proportional to actually 1 over our kinematic viscosity, and then also some information about length scales over which it's operating. So viscous diffusion acts in general to slow flow down, and that would seem to make it an incredibly simple term, something that just damps the flow and slows it down. But what we'll find is that, to our surprise, viscosity can actually create flow. It can create vorticity in the flow, especially with interactions on boundaries. It leads to the rich phenomena of turbulence, and is really one of the main reasons that fluid dynamics is such a fascinating subject and an open and unsolved problem as we apply it to turbulent objects like planetary atmospheres and astrophysical objects.